Hello everyone, my name is Joseph Carey and my project is to solve 3D printing starts and stops using double-edged Eulerian graphs. My mentor is Janet Beckham from San Jose State University in the Mathematics and Statistics Department, and coordinating this project is Ray Morales at the Gavilan College Biology Department. So what does 3D printing projects have to deal with our problem? Well, first we have to discuss about what 3D printing is. In 3D printing, we have an extruder head releasing some type of filament, like plastic, metal, or concrete, that travels along the path of an object layer by layer. These layers are interpreted as 2D shapes with pathfinding algorithms to traverse the polygon for efficiency and rigidity. However, there are currently 3D printed parts that show holes or breaks in the part, as the source of the problem is to be shown with starts and stops within the printing process. The purpose of this research project is to find a method of continuous traversal through the slices of 3D printed objects, such that stops and starts cease to occur in the first place. Finding such includes using some graph theory on a 2D plane with the slice portion of an Eulerian circuit. Once we find one of these Eulerian circuits, we can solve the problem and have a continuous traversal method to solve more of these complexities. So we've been making 3D printed objects for quite some time now, from our at-home printers to massive projects in the construction industry. So we've already thought of some ideas to make precise prints with respect to efficiency. However, 3D prints are now becoming more advanced, so we now have to make some modifications with our known algorithms and techniques to accommodate these more complex ideas. 3D print breaks are occurring more frequently when we have a traversal pause as the extruder stops outputting filament, showing that there is a non-continuous path of the printer head. This is shown in the figure on the right, where our top portion is a layer of 3D print, and the bottom portion is one of these holes occurring. Notice how along this green continuous path, there are these pink starts and stops along with these printer head jumps. This is where these holes occur the most, because the printer head, as it traverses from one point of the print to another part of the print, it ends up cleaning itself and possibly causing a malfunction to occur. And the more complex you have these geometries in these 2D layers with these holes and breaks, it causes more occurrences for them to happen. So we must change our traditional methods to solve these more complex problems. So how do we solve the problem? Well, we have to find an Eulerian circuit such that traversing the graph does not cross any edges, shown in figure 2, and traverses each edge exactly once. In fact, by the definition of an Eulerian circuit or an Eulerian graph, each edge must be traversed exactly once. So then we can create an algorithm that is tested and performed by creating a path with these two specified conditions, along with no vertices touching each other. In fact, the algorithm and the computer, all it's concerned with those two aspects is the vertices can be exchanged multiple times, but the edges have to be exactly once. But in practice, these extra vertices, when it travels back to a existing vertex being used, it doesn't technically go back to it. It travels very close to the other one, essentially merging the two vertices together while maintaining a continuous path. So when we were trying to figure out how to conduct our research, we have to find Eulerian trails and circuits to understand how they work. Then we have to figure out some previous situations when a graph is non-Eulerian, and how would we go about solving one of those with our known understanding at that point in order to stop the starts and stops causing these breaks. From there, we would have to start modifying our known ideas with our known algorithms and techniques from the research provided to produce an effective algorithm. And from there, we have produced an algorithm that has been tested and perfected to solve the problem. As shown, we have our produced algorithm here. It starts off with a regular, simple graph, although it can be complex in the first place, and essentially double every edge, so that way all the edges can now become Eulerian. That means any graph that can be inputted, no matter how complex, can be solved. From there, we would just have to set some variables and determine where are we starting from in the graph with our set conditions. The first is we would have to set our orientation, whether it's going to the left or right of a starting vertex. It cannot go downward unless it is absolutely necessary as our last resort option. From there, we would have to see what type of edge can cause a disconnection as we're going through the algorithm. Another condition that we need to satisfy to not cause any disconnections. And then from there, we have to figure out what part of the graph are we going to next while satisfying no crossings and no repeated edges as well, along with having vertices not being technically reused, though we are still reusing them, but by the algorithm standpoint, it can be reused. And then from there, we would just have to keep going through this process by checking if we have every vertex and every edge set, so that way we have found our desired circuit. So let's go ahead and check out some examples and see how this works in practice. Here's one of our examples in figure 3. Notice that this graph is non-Eulerian. How is it non-Eulerian? Well, all of the edges that are connected to the red vertices have an odd amount of vertices, whereas in blue has an even amount. So to make this Eulerian, we have to double all the edges. Now all the edges are completely blue. Every edge has an even amount of vertices and edges connected to each other. And then from there, we can start at any vertex. In this case, we started at this vertex as a boundary vertex. And we can choose whether to go left or right. In this case, we go left. Now, there are some more options after this point when we pick the other vertex. The algorithm would like to come back to the original vertex to create a leaf as shown in figure 4. However, another satisfied condition that has to be required is to not go downward unless it is absolutely necessary. In this case, there are other edges that could have been used before going downwards, as in this case, we only have one edge that can go downwards in figure 4. So we can choose another way to go through this algorithm as shown in figure 5, where all the edges can go around, and as soon as able to go back to left or right on the bottom of the graph, then it can return back. From there, we have this type of graph here, where all the edges in this part are all connected and directed. This is what the computer and the algorithm think, is all the vertices can be reused, but all the edges are essentially only used once. But in practice, all of these edges are not connected to each other along with the vertices associated. So that way we have a continuous path from point A back to basically point A from the starting vertex. Another example is with this more complex example where we have 12 vertices that are all of odd degree. All of these edges have 3 or 5 or odd number sort of edges. So like previously, we would double every edge so that way all the edges can be Eulerian and create an Eulerian graph. From there, we can pick any edge we'd like to. In this case, we have picked one of the corner edges and had to go all the way to another part of the graph and continue on to create a leaf in this case, but at the same time, not going downwards unless it is absolutely necessary. Even though it's going in a diagonal, it's still going left. And then from there, we have created our final graph, very complex, but very continuous. So in conclusion, we have solved breaks and holes by knowing where they come from and how to avert them with an algorithm and an Eulerian circuit by modifying the input graph. After some research and improving 3D printing, modifying these existing ideas have helped us find an algorithm with a continuous path. Our algorithm has increased flexibility towards design, as doubling the amount of edges creates more designers to explore how rigid their 3D prints can become by their thicknesses. Improvements on previous algorithms by taking advantage of Eulerian properties in graph theory have now proven that our algorithm can help in efficiency and simplification of design for future 3D prints. I'd like to say some acknowledgements. I would like to thank Sogol Jenna Beckham for guidance and exceptional mentoring of the material. A special thanks to the Gavilan STEM program and San Jose State University for allowing extended time for the project, and funding for this project has been provided by the Gavilan STEM program and project sponsored by San Jose State University. And thank you all for listening. Have a good day.